Welcome all. In today's class, we discuss about reactivity and orientation in electrophilic substitution reactions. In the previous few classes, we have discussed about electrophilic substitution reaction taking place in benzene, where we discussed five important reactions, namely halogenation, nitration, sulfonation, Friedel-Crafts alkylation, as well as acylation, where it was the reaction of bare benzene, that means benzene without any substituent. Here the question is, what if benzene is already carrying a group? Then two questions arise. Suppose, we know during electrophilic substitution reaction, one hydrogen on benzene ring is replaced by various groups during electrophilic substitution reactions. Now what if benzene carries one group already? Like this, you have a group here, some functional group. Then two questions comes. One is, what about the reactivity or rate of reaction? Whether the presence of this group will increase or decrease the reactivity compared to benzene itself. The second question is more important. That is, where does the substitution takes place? The site of electrophilic attack, or what we call orientation. We can see that with respect to this group, the positions can be classified or named like this is ortho position, that is the adjacent position. This is meta position, that is alternate position. And the last one, this is para position or opposite position. So where does then substituent comes is a question. Now, based on the nature of the group, it can be mainly of two types. This group can be either electron donating or electron withdrawing from the ring. We will take different cases. Look at this chart. There are mainly two types of groups. One is activating group and the other is deactivating. The groups coming under activators, you can see strongly activating, moderately activating, and then deactivating groups are there. Some are strongly deactivating. So here activating groups means these groups supply or donate electron to the ring, so that benzene ring become more electron rich, so that it become more susceptible for electrophilic reaction, electrophilic attack. Whereas the other set of groups, deactivators, here the functional groups are electron withdrawing, so that they reduce the electron density of benzene ring. So you might remember the mechanism of electrophilic aromatic substitution reaction, where the first step is attack of the electrophile on the ring. So the electrophile is looking for electron rich center. If the electron density in the ring decreases, then the reactivity also decreases. So broadly, there are two categories or two classes of functional groups, with one exception, that is halogen is an exception. They exhibit mixed behavior. They are deactivating, but they are orthopara directing. Here, see, the activating groups reduce the reactivity, and they will show ortho-para orientation. Whereas the deactivating groups are decreasing the reactivity and they are meta-directing. So this go hand in hand. Activating groups are generally ortho-para directing. Deactivating groups are generally meta-directing as far as electrophilic substitution reaction is concerned, with an exception of halogen, which are basically deactivating but ortho-para directing. Let us take one by one. First one, we consider activating and ortho-para directing groups. These are basically electron donating groups. That's why they are activating. Here the functional groups you can see. In the first line, NH2NHR, that's amines and primary, secondary, tertiary amines. Then OHOR, phenolic groups. They are characterized by lone pairs on the heteroatom nitrogen or oxygen, which when connected to the benzene ring will have a resonance effect, plus R effect. That's why they are strongly activating. And the second one, the second category, that is the second type, moderately activating groups. For example, this NHCOR, that is amide linkage, why it is moderately activating? You can easily understand. See, nitrogen is having a lone pair, right? And this is the amide linkage. When this is connected to benzene ring, the lone pair on nitrogen will be, then lone pair is conveniently shown like this. So this lone pair is conjugated to the ring on one hand. At the same time, this lone pair can be delocalized to this side also. So unlike aniline, where there is no acyl group, the lone pair is fully flowing to the ring. But here in this amide linkage, lone pair is partially withdrawn by this acyl group or this carbonyl group. That is why the activating power is reduced. That's why this amide group is, or you can say anilide group, when it is connected to benzene, it is only moderately activating. Same reason for the ester group. Then weakly activating group, that is alkyl and aryl groups are weakly activating. So what happens when these groups are attached to benzene ring? These groups increase the electron density in the ring, making it more susceptible for electrophilic attack. See, any of these groups when connected, they are donating electrons to the ring by plus R effect or plus I effect, etc. So electron density increases in the ring. So when the electrophile comes and attack the ring, it will find it more easy, or the reactivity increases. That's why they are called activating group. They activate the benzene ring for an electrophilic attack. That's the meaning. Now second point is they are ortho-para directing, because if we look into the resonance structures, we can see that electron density is more concentrated at ortho and para positions compared to meta, so that electrophile preferably attack ortho-para positions. Let's understand this point more clearly in the next slide. You can see, for example, aniline is taken here and look at various resonance structures. You can see the lone pair on nitrogen is delocalized into the ring, and you can see that considering various resonance structures, these three structures, if you look closely, you can see negative charge appears at the ortho and para position. Here there's negative charge, here there's negative charge, and here there's negative charge at ortho para positions. So during the mechanism, electrophile will preferably attack there. That's why activating groups are ortho-para directing. It's very clear. Generally, substitution takes one place at a time. That means mono substitution takes place. So the product may be ortho product, ortho substituted product, as well as para substituted product. But if the activating group is highly activating, strongly activating, then substitution can take place at all positions. That means to ortho position as well as para position. In that case, you get 2, 4, 6 tried substituted product. That happens in the case of aniline, phenol, etc. and similar substituted compounds. But if the group is only moderately or weakly activating, then you will be getting ortho product as well as para product. A mixture of the two products will be obtained. Now coming to the second example shown here, this is how methyl or alkyl group connected to benzene becomes activating group. See, methyl or alkyl group has plus psi effect, which diminishes with distance, we know. But more than that, when methyl group is connected to benzene, it has another effect here which is depicted in this diagram. What is this? You may recall. See, remember, actually what we are discussing in this session has already been discussed in the other chapter under resonance. Applications of resonance, where we have discussed how the reactivity of benzene ring changes due to resonance, plus R and minus R effect. You may refer back to those topics, and the concept which you have learned there is applied here. Also in hyperconjugation, see, when you have an alpha hydrogen connected to a double bond, it has hyperconjugation. So it's also called no bond resonance. So we have drawn 3 hyperconjugative structures, and here also you can see that negative charge appear at ortho para positions, right? At ortho para positions of benzene. So toluene also is ortho para directing, and it is only weakly activating because this hyperconjugation is not as strong as resonance effect, it is only weak. Anyway, when toluene is taken for electrophilic aromatic substitution reaction, it will be more reactive than benzene, and you will be getting ortho substituted as well as para substituted product. Let's take now examples. Here, first of all, aniline is taken for bromination. Bromine water is used, polar solvent. You get 2,4,6 tribromoaniline. Why? Because NH2 is highly, strongly activating group. Coming to the next, toluene is taken for Friedel-Crafts alkylation, isn't it? Yes, it is Friedel-Crafts alkylation, and you are getting ortho silene. What is silene? 1,2-dimethyl benzene is commonly called silene. Orthosilene as well as parasilene. You get 2 products as a mixture. Here, tri-substitution doesn't take place because methyl group is not a very strongly activating group, it's only a weakly activating group. Now coming to the second category, deactivating and meta-directing. Here, these are electron withdrawing groups, right? It may be strongly deactivating or moderately deactivating. What is their speciality? We have already discussed these things in minus R effect, if you remember. These groups are characterized by, for example, if you take, you can see that, for example, CN is actually C triple bond N. Aldehyde group is C double bond OH. like this it comes, you can see that all these groups have got multiple bonds, double bond or triple bond, and connected to an electronegative atom. So what? The pi electron will be attracted towards this electronegative atom easily and get delocalized, and that will be extended to the ring. That means all these groups withdraw electron from benzene ring due to this minus R effect, so that these groups decrease the electron density in the ring, making benzene ring less susceptible for electrophilic attack and decreasing the reactivity. Sorry. Okay. Yes. So the reactivity decreases. Since electron density is particularly reduced at orthopara positions, electrophile preferably meta position. So these deactivating groups are meta directing. Why? We can easily understand it from the next slide. You can see here the minus R effect operating in nitrobenzene. NO2 group is strongly deactivating. When it is attached to benzene ring, you can see the pi electron density is going out of the ring. NO2 group withdraw electron density from the ring. And in these resonance structures, you can see, that is 2, 3 and 4, you can see there is positive charge appearing at the orthopara positions, right? What does it mean? When there is a positive charge, it means electron density is decreased. So electron density has decreased particularly at orthopara positions due to this minus R effect of NO2. So relatively the electron density is more at meta position, because at meta position there is no positive charge. So relatively electron density is more at meta position, and the electrophile will now attack the meta position. So these are meta directing, correct? Let's take example. See, benzoic acid is taken for nitration. So what happens? The nitro group, NO2 group, will attach to meta position, or the electrophile will be attacking the meta position. Preferably you get meta nitrobenzoic acid. But remember, this reaction is little difficult because COH group is deactivating group, so reactivity has decreased compared to benzene itself. So you may require a very high temperature and long time for the reaction to take place. The second example, nitrobenzene is further nitrated. What do you get? You get meta-dinitrobenzene. Why? Because NO2 is deactivating and meta-directing. So the next group comes at meta position. So remember that here the reactivity decreases due to this deactivation. It is found that if you take benzaldehyde for Friedel-Crafts alkylation or acylation, practically there is no reaction taking place. Friedel-Crafts reactions are not possible with strongly deactivating groups in benzene ring, which is an indication of how these groups reduce the reactivity. We have an exceptional case of halogen. Halogen, fluorine, chlorine, bromine, iodine, when connected to benzene, it has two effects operating at the same time. See, we know halogen when connected, for example, if it is Cl, chlorine, halogen has got three lone pairs, there are three lone pairs all around, okay. So you know that halogen is most electronegative, so it has minus I effect operating through the sigma bond, which we have already learned. Cl will be withdrawing electrons through the sigma bond. At the same time, due to the presence of lone pair which is in conjugation with benzene ring, this lone pair can get delocalized into the ring also. That is plus R effect. So two effects are operating simultaneously. One is minus I effect, in which electron density is withdrawn by Cl from the ring, and the next is plus R effect. There's a lone pair on halogen is going to the ring. So these two effects operate simultaneously. So what happens? It has a mixed behavior because there is a competition between two effects in opposite direction. So it is that as far as reactivity is concerned, minus I effect is more predominant, or it is more decisive as far as reactivity is concerned, and it is deactivating due to the minus I effect. Electron density decreases due to minus I effect, so react rate decreases, right? Because minus I effect is more predominant than plus R effect as far as reactivity is concerned. But for orientation, plus R effect is more predominant or more selective than minus I effect, so that attack takes place at orthopara position. So it is orthopara directing. Basically, chlorobenzene is less reactive than benzene itself, but if at all reaction takes place, it will be at orthopara positions, right? Look at the example. Chlorobenzene is nitrated, you get orthonitro and paranitrochlorobenzene, a mixture of two products, because it is deactivating, so reaction is difficult to take place, and if at all it takes place, it will be at ortho and para positions, one at a time. So we have learned in this class about reactivity and orientation of electrophilic substitution reactions in mono-substituted benzene. There are mainly two types of functional groups. One is electron donating groups, which are activating and orthopara directing. The second category of functional groups are electron withdrawing groups, which are deactivating and meta directing, with an exception of halogen, which are deactivating due to minus I effect and orthopara directing due to its plus R effect, which operates simultaneously. You have few questions to answer. You should write answers for these questions in your notebook. Which is more reactive towards electrophilic substitution, benzene or benzaldehyde? Give reason. What happens when toluene is treated with concentrated nitric acid and sulfuric acid? You have to give the reactions or equations. And third question, phenol is more reactive than benzene towards electrophilic substitution reaction. Why? Thank you.